So I think we can start now. We have Honorable Shafik there, with Khaled Gabriela, Martin Garcia with us. And we also have, I assume, our India's ambassador to Bolivia. I worked with INSART to get together for this virtual workshop on soil and water conservation for resilient agriculture under climate change dynamics in Latin America. This workshop addresses an issue that lies at the heart of agricultural sustainability in Latin America, in Asia, in India, and the entire global south in particular. Soil and water conservation for climate resilient agriculture under changing climate conditions requires urgent and evidence-based action. Latin America today, the agricultural landscape in Latin America is diverse yet highly vulnerable, comprising rain-fed, highland, coastal, and dryland systems, many of which are dominated by fragmented smallholder cultivators. And when I look at the situation in Latin America and in Bolivia, I find a lot of similarities with India. We have similar challenges as there are in Latin America because of climate change. And soil and water are the two key components which can help us move towards resilient agriculture. Only last week, on the 5th of December, the global community marked World Soil Day, emphasizing that soil health is fundamental to food security, climate resilience, and sustainable development. Today, the workshop builds directly on that momentum with a specific focus on strengthening soil health, soil moisture regulation, and water resource management through agricultural, technological, and policy innovations. So these innovations are the topic of discussion today between us. We have divided our work program for the next 2 hours into 3 parts. We will have an inaugural session where we will invite my partner from INESTAD, Dr. Hernandez, to give some opening remarks, after which we will have inaugural addresses by the Indian ambassador to Bolivia and the Bolivian charge d'affaires in India. Following this, we will move into a dedicated session on the situation in Latin America, which Dr. Hernandez will steer for us. And then we will go into conversations from the larger Global South community on the same issues, which I will moderate. So let me welcome all of you again from all parts of the world and request my partner, Dr. Beatriz Hernandez, to give her opening remarks. Over to you, Beatriz.
Thank you very much. I would like to greet all participants and begin by expressing my sincere appreciation to the DAS team for the kind invitation to join lead host this virtual conference. Can you hear me?
Yes, we can hear you.
Yes,
okay.
We can hear you.
Yes, we can.
I'm grateful for the opportunity to reflect together on an issue that is key for our region. As we know, across the Global South and in Latin America in particular, smallholder farmers are confronting a growing set of challenges. As you said before, climate variability and climate change are reshaping their environments through concentrated rainfalls, prolonged droughts, and increasingly unpredictable weather patterns. At the same time, land degradation continues to threaten agricultural yields and consequently rural livelihoods. Yet smallholder farmers remain at the heart of the global food system. Their role is not only indispensable, but strategic. According to the Food and Agriculture Organization, for instance, small-scale farming units employ nearly 30% of the world working population and produce more than 80% of the world's food. Therefore, strengthening these actors is imperative. In this context, the exchange of knowledge and experience becomes fundamental. Public policies, programs, and collaborative initiatives must support smallholder farmers in adopting sustainable agricultural technologies to improve productivity, restore soils, and build resilience. But to be truly effective, this solution must be not only agronomically sound, but also economically viable. For instance, cost effectiveness is very important, and as well as culturally appropriate. Small farmers must be able to adopt them, benefit from them, and make them their own. This requires a multidimensional lens. Only by integrating these dimensions, we can effectively support smallholder farmers. I hope that today's dialogue will inspire concrete actions, new collaborations, and a renewed commitment to build a more sustainable and resilient agricultural future for the global south. Thank you very much.
Thank you, Dr. Hernandez. Thank you very much for your opening remarks. Let me now, I have the privilege and honor to invite our India's ambassador to Bolivia, His Excellency, Mr. Rohit Varmana. Over to you, uh, Mr. Varmana. The floor is yours.
Thank you so much. Namaskar. It's my pleasure to be part of this virtual workshop on soil and water conservation, which is related very much to our agricultural collaboration between India and Bolivia. Most of the participants here might be aware that Indian Embassy is very new in Bolivia. We started working from at ambassador level, started working from March this year, and almost 8 months I have been there as the first ambassador. While setting up the Indian Embassy, we had the Herculean task of engaging with government, not only at the national level, but also the 9 diverse departments which are very, very active in Bolivia. So we as mission started engaging there. And one area that came up very interestingly and very enthusiastically from all the interlocutors to us was agriculture. When I visited Santa Cruz, uh, when I visited Beni, when I visited even Oruro or Sucre, each and every department, they were interested in collaborating with India on agricultural field. I had the honor of spending 2 days with Honorable Vice President at that time on the Isla del Sol, Sun Island in the mid of the highest lake in the world, that is Titicaca. And Honorable Vice President told me that we need to do some joint research together. Interestingly, most of the people would know that Bolivia is home to more than 1,500 varieties of potato. We have varieties of maize there. We have lots of production of soy. We have production of chia seeds and many other agricultural products. The land is vast. For example, if you go to Beni, there is lots of water and lots of land. But if you go to Oruro, again, the land is there. Sucre has lots of land, but the topography differs. And all the types of high altitude challenges that we see in India are being seen in Bolivia as well. And therefore, I believe that with vast potential of Bolivia's land mass available there, skilled people there, and as well as the climatic condition which supports agricultural production, I think that Indian industrialists, Indian investors, Indian farmers should look at Bolivia for investment and collaboration and partnership perspective. And on and the national government of Bolivia, how can we collaborate? And there are many opportunities. One collaboration certainly is on research and joint study. And this workshop, I believe, will be very helpful in creating areas which can be helpful for us to engage with Bolivia on all these fields. I'll give you one example that ICAR can collaborate with the Bolivian side for doing some research. We have high altitude research institution in agricultural field. We have lots of research being done in India on the cattle and livestock that can be shared with Bolivian side, and we can certainly work together to promote it. Therefore, when RIS and INESAR join hands to conduct this virtual workshop, my belief is that this is first step in moving together in agricultural collaboration. I see the representatives will be speaking from ICAR, and they would be sharing their insights. There are policy making institutions, think tanks, as well as the specialist field officers or experts in agricultural field who can be very relevant in today's workshop to share their insight and guide us, guide diplomats, guide the governments, how we can take this forward. So I certainly remain attentive, and my colleagues are joining from my embassy as well as ministry. We will be taking notes of the recommendations. I will also request RIS and INESAD to kindly share with us the outcome of this webinar, virtual workshop, and sorry. Can
Yes,
you hear
please
me?
go on.
Yeah.
Yes, we can
So-
hear you.
Yeah, virtual, please share with us the result or outcome of this virtual workshop, and it will be very, very helpful for every one of us. I propose that on agricultural side, we should have echo is coming from RIS.
Sorry, your voice is echoing.
Can you mute on RISGP, please? Yeah, perfect. So I believe that once we have this workshop and its outcome, it will guide us, the policymakers, diplomats, as well as the governments to move forward to take some more steps which are more concrete towards water, soil conservation and collaboration in agricultural side. Climate change is a universal phenomenon which every one of us is facing in India as well as in Bolivia. The temperature is changing there, the pattern of rainfall is changing there as well, and everyone is concerned about that. But when I share with them the varieties of rice, for example, India has developed, and how we become world's one of the largest producer of rice and one of the largest exporter of rice, Bolivia wonders how India, having 1.4 billion mouth to feed, still can export rice and other food grains. But that is the reality, and that I and we all know is because of the scientific inventions and scientific research that we are undertaking in India, which Bolivia certainly can benefit out of. So my proposal is that after and as outcome of this workshop, we take some concrete actions and we join hands for the mutual benefit. As I said here, Bolivia has vast land which requires lots of investment, which requires technological and mechanical machinery inputs so that we can utilize that land for more agricultural production. If India and Indian investors and farmers can be part of that initiative and go there, take land, join hands with Bolivian partners and produce food grain and other agricultural output, even cash crop, perhaps both countries will benefit out of that. Our investment, our technology, our research, our scientific progress can certainly help Bolivia in increasing its production, which will not only help in feeding the Bolivian population, but also increasing the export and thus earning the forex for the Bolivian partners as well as our Indian investors. So that is my main proposal here in this webinar. And of course, the all participants will share their views regarding from scientific perspective, from policy perspective, but as a diplomat, I shared my perspective from collaboration perspective, from partnership perspective, how we can partner between the two countries. And I look forward to hearing from others. My colleagues will certainly continuing with this. I am traveling, so I will be off and on in this webinar, but it is certainly my pleasure to join all of you. And I consider this is an excellent opportunity. This should be first in the series, and I would propose INESAD and RIS to take forward this step and continue to engage with each other. High Commission, Embassy, every one of us will be part of that, and we would encourage you to conduct more such webinars on different topics. Thank you so much.
Thank you. Thank you very much, Ambassador Wadhwana. This was wonderful. You know, you have been in Bolivia for such a short period, and yet you have already gathered substantive information about the very topics that we are dealing with today. We are also thankful to you for offering to collaborate to help us in taking the joint partnership of Dakshin and INASAD together and forward, and also your guidance in respect to the various conversations you've already had, including with the Vice President, the then Vice President, on some of the areas of collaboration. And your suggestions. We also have from ICR Dr. D.V. Singh, Dr. Dharamveer Singh. He will be representing ICR, and his areas of specialization are the very areas that we are discussing in the next 1.5 hours, which include soil health management and watershed management. So we will be looking to hear from him. But first, now, as the last part of the inaugural session, I would request Her Excellency, Madame Aled Gabriela Bustamante Garela, to give her inaugural address. Over to you, Excellency.
Thank you so much. I don't know if you can hear me well.
Yes, we can hear you.
Okay. Well, distinguished Ambassador Rohit Badwana, it's my pleasure to see you here. All the organization, the experts, the colleagues from India, Bolivia, and the Global South, RIS, INASAD, ICAR. It's for me and from the Embassy of Plurinational State of Bolivia to join. It's an honor to join this important dialogue and on soil, water, and conservation for climate resilient agriculture. Well, Bolivia is facing increasing climate pressures right now. Severe drought, soil degradation, and extreme weather events that directly affect smallholder farmers. Our farmers are the most affected by this change of climate. Also, our rainfall systems and rural communities are affected by these climate pressures. These challenges compel us to integrate watershed management, efficient irrigation, soil conservation practices, and climate-informed agricultural planning. Those areas in which Bolivian institutions have contributed valuable in the research and evidence. In this context, India stands as a key partner. India's experience in climate-smart agriculture, water harvesting, micro-irrigation, community water governance, and the restoration of the soils offers significant insights for Bolivia. So in recent years, we have begun advancing technical exchanges and exploring new areas of collaboration between our countries that can support a rural development and agricultural resilience in both countries. This workshop, this event, provides an important opportunity for us to deepen our cooperation under the framework South-South collaboration. It's important, allowing us to learn from shared challenges and adapt successful practices to our respective realities. Bolivia also wish to propose, if it's possible in this event, to talk about the initiative focused in restoring vulnerable watersheds and improving water efficiency for our small farmers. We see great value in combining Bolivia's ecosystem knowledge in innovative practices to create a practical pilot that strengthens community resilience to face the climate change. We stand ready to move this proposal forward together, and we can work on that. Also, Bolivia reaffirms its commitment to working with India, with Latin America, and the Global South to build a more resilient, sustainable, and inclusive agriculture future. On that matter, protect our soils, safeguards our water resource, and strengthens the livelihoods of our communities. I want to thank you, and I would also like to inform that I will be no longer to stay for the full duration of this conference, as I'm currently representing Bolivia at the UNESCO event here in Delhi, and I must return to the event. But thank you so much for the invitation. Thank you so much, the organizer, for this workshop, and thank you for understanding. Danieva, and I hope this event have a successful conclusions. Thank you.
Thank you. Thank you very much, Excellency. No, this is very encouraging. These are very encouraging remarks from you. We really appreciate that you could take time out to join us at the beginning of this very interesting conversation. We note carefully that your interest, or Bolivia's interest, in India's experiences in climate smart agriculture, in micronutrients, micro irrigation, and also your asking us to also talk about water efficiency. We would certainly be, that is a part of the conversation that we're going to have. As I mentioned, Dr. D.V. Singh would be talking. He's an expert on watershed management. He would be talking about it. But thank you very much for joining us and enlightening us with not only the interest of Bolivia, but also the specific areas in which you would want us to take these conversations forward. We will certainly do our best with the help of your mission and our mission in Bolivia, as well as the two partners, Dakshin and INESAD. So now we can shift to the next part of the conversation, where we will have the Bolivian landscape discussed in the first instance, where we talk about soil and water conservation for resilient agriculture and what is required for that in Bolivia and what are the experiences. So may I then request Dr. Hernandez to take over. Before that, I would just inform you that we have a Spanish translation available. We have Vidushi with us in the room. Vidushi, if you could raise your hand. So she's available for translation. So Beatrice, please do mention to us in which of the interventions you would like Vidushi to translate for us, so that we can take careful notes, and also the non-Spanish speaking people can understand what is being said. So over to you, Beatrice.
Beatrice, you are muted.
Very sorry. Okay, you can listen to me right now. Okay, we would like to present actually a case study of quinoa production, whose methodological framework, and analytical tools combine agronomic, climate, economic, sociocultural, and impact evaluation dimensions. I think that it is very interesting and relevant because of the process. We have worked over 3 years from research, action, and structure, and we believe that serve as experience in other contexts in the global South. So let me introduce first Oscar Kolke. He's our senior researcher at INESAD. He's a senior agricultural engineer with over 25 years of experience in agricultural development and research, which is strong focus on soil fertility and crop nutrition. His professional background includes work at several institutions such as the Tropical Fruit Validation Center in Argentina, the University of Costa Rica, also in Tagre in Mexico, and of course many institutions in Bolivia. He's also the creator of the BCA Services software for soil analysis interpretation. And Oscar holds a specialization in plant protection and seed technology from the Federal University of Pelotas in Brazil, along with diplomas in business management, agribusiness, and higher education. He has taught at the postgraduate level in several Bolivian universities. He has produced extensive technical and scientific work, including books, articles, and manuals. Oscar is going to speak in Spanish, so we need to translate to English, please. Oscar, puedes comenzar. Hola, Oscar, ¿estás por ahí?
Sí, Beatriz, gracias. Muchísimas gracias por la presentación. ¿Me indicas si se logra ver?
Sí, se ve. I don't know if it is the translation is beginning.
We can hear you. Bueno, antes de iniciar, voy a referir una frase relacionada a la presentación. La materia orgánica es la base de toda la fertilidad del suelo.
Señor, ¿es posible que lo repita, por favor?
Inicialmente, había comentado de que voy a arrancar con una frase, la cual es que la materia orgánica es la base de toda la fertilidad del suelo.
He said that he's going to start with each sentence and I'm going to continue in that manner. So he said that the organic material is the base of soil fertility.
La presentación, el trabajo está referido a un análisis de fertilidad de suelos en parcelas de producción de quinoa orgánica en comunidades del Altiplano Sur de Bolivia.
The work's principal aim is about soil fertility analysis in organic quinoa production in the communities of southern Bolivian Altiplano.
Este trabajo ha sido realizado en comunidades del Altiplano Sur de Bolivia.
This work was basically realized, which was implemented in the communities of Bolivia.
En la parte de introducción refiero de que una de las especies emblemáticas de la producción orgánica en Bolivia es la quinoa.
One of the basing the work and its production, one of the principal cultivars, the cultivars were organic production of quinoa.
A nivel nacional, en Bolivia existen más de 120,000 hectáreas de quinoa cultivada.
In Bolivia, there exist about 121,119 hectares of land of quinoa.
Durante el periodo de 2018 y 2022, el rendimiento promedio de Bolivia de la quinoa fue de 517 kilogramos por hectárea.
Between the years of 2018 and 22, the average yield in Bolivia was 517 kilograms per hectare.
Sin embargo, en el mismo periodo, Perú y Ecuador aportaron rendimientos de 1,477 kilogramos y 1,083 kilogramos respectivamente.
Between the same years, the same period, the countries Peru and Ecuador, they reported yields of 1,477 kg per hectare and 1,083 hectare per kg simultaneously.
Bueno, eso implica de que el rendimiento comercial de la quinoa es bastante reducido comparado con los países de Perú y Ecuador.
Which implies that in Bolivia, the commercial production was much higher than the countries of Peru and Ecuador as comparison to these countries.
La menor productividad de la quinoa está relacionada con la pérdida de la fertilidad del suelo.
It's basically related, its production is basically related to the soil fertility of land, which is in Bolivia.
Originado particularmente con el agotamiento de la materia orgánica y los nutrientes del suelo.
Basically relating originally to the soil, the organic material that is available in the soil,
así también como la reducción de la biodiversidad del suelo.
and in the same way, the biodiversity of the soil and the land.
Bueno, el trabajo se realizó con el objetivo de analizar la fertilidad de suelos en parcelas de producción de quinoa orgánica en comunidades del altiplano sur de Bolivia.
The main objective of this work was to analyze the soil, analysis of soil and its organic production.
De manera resumida, indicamos que la región donde se hizo el estudio es una zona categorizada como un clima desértico.
In conclusion, in resume, we can say that the work that was realized in these regions of the land was categorized on the basis of the desert climate of that land.
Bueno, la precipitación en esta región apenas llega a 200 milímetros por año.
Perdona, ¿ha dicho 7?
No, la precipitación en esta región apenas llega a los 200 milímetros de lluvia por año.
So he's saying, okay, the rainfall in these areas occasionally reaches to 200 millimeters.
También se registran por lo menos 200 heladas por año.
And it's also registered, is also documented as 200.
Entonces, está bien, de acuerdo. La altura donde se cultivan quinoa en sistemas de producción orgánica están entre 3.700 metros a 3.600 metros sobre el nivel del mar.
The altitude that it reaches is about 3,718 meters above sea level.
Bueno, entre los resultados más importantes de este estudio,
among the most important results of this study, of this work,
los suelos se categorizaron como arenosos.
the soil was categorized as fertile.
Como suelos arenosos. Franco-arenosos un 68% y areno-blancosos un 27%.
As sandy loam for 68% and loamy sand as 27%.
Bueno, en el lado derecho tenemos una figura estadística que nos muestra que el pH del suelo tiene predominancia de suelos alcalinos.
On the right side of the presentation, we can see the strategic figures of pH level of the soil, which is very high as 67%.
Uno de los resultados más importantes de este estudio fue cuantificar y determinar que el principal factor de la baja fertilidad es la mínima cantidad de materia orgánica en el suelo.
One of the most important results of this study was to quantify and determine the principal factor, which was the minimum availability of organic material.
El 97% del suelo tiene muy bajo contenido de materia orgánica y muy bajo contenido de nitrógeno.
Okay. So the organic matter of this soil was very low, around 97%, 97%,
Sí, perfecto, 97.
and the total nitrogen was also 97%.
Bueno, aquí tenemos unos mapas que nos muestran la fertilidad del suelo, ¿no? Entonces, casi el 100% de los suelos tienen muy baja fertilidad.
Here we can see the maps of the fertility of soil, and as you can see, that's very low. It's about 100% of the organic material.
Tenemos una comparación de un estudio realizado hace 15 años en la que la materia orgánica tenía mayor contenido. Las barras
We have a
verdes
comparative.
son,
Perdón.
las barras verdes son el estudio reciente realizado por INESAT y las barras verde claras son de hace 15 años, del 2008.
Here we have a comparative study of around 15 years ago, wherein the organic material basis, as we can see in the presentation, is low and moderate, about 37% and 50%.
En este periodo de los 15 años, la materia orgánica se redujo de 2,64% a 0,47%. Y eso equivale a una pérdida acumulada de 65 toneladas por hectárea en 15 años.
As you can see, in these last 15 years, the organic material was equivalent to 2.64 up to 1.23, and on the other side, 0.47 to 0.25, which was an equivalent to an accumulated loss of 65 hectares.
En base a ese estudio, en base a todo ese diagnóstico, pusimos un plan de acción, implementamos unas parcelas demostrativas, pero antes de eso efectuamos un compostaje en el altiplano.
On the basis of this diagnostic study, we based an action plan.
Ese proceso de compostaje se realizó en pleno invierno, con resultados bastante favorables, porque en 4 meses logramos hacer un compostaje que normalmente se hace en un año.
The compost was implemented during the months of winter, which was a favorable climate, and they were able to make the outcome in 4 months as compared to the number of years. ¿Ha mencionado los años?
El compostaje normalmente se hace en más de un año en el altiplano, pero con este trabajo logramos optimizar en 4 meses.
So in Antiplano of Bolivia, normally the compost takes more than a year, but on the basis of this action plan, they were able to conquer it within 4 months.
En la parte inferior tenemos unos resultados donde mostramos claramente que el proceso de compostaje ha sido positivo en la mayoría de las parcelas. Hemos visto cómo se ha incrementado aplicando el compost localizado y de paso en cantidades adecuadas. Entonces, este trabajo ha permitido ver puede incrementar la productividad de la quinoa utilizando un material, un abono compostado y una aplicación localizada.
On the basis of this action plan, as you can see, there were favorable and positive results on the basis of use of compost, which increased the availability of compost and productivity of quinoa.
También hicimos una prueba para verificar que el compost tenía un efecto positivo. Y en resumen, acá tenemos el efecto de diferentes dosis de compost, su efecto en el rendimiento.
There was also another trial, a test that was done to verify whether this compost was positive, and on the basis of this doses of compost,
Finalmente, las principales conclusiones que encontramos fue que el principal problema de todo este estudio es que hay deficiencia de materia orgánica.
on the basis of the conclusions that were taken out from the action plan and work generated were soil fertility analysis, which on the basis of which was concluded that there was enough organic material.
Y entre las recomendaciones tenemos de que se debe optimizar el proceso de compostaje y hacer una aplicación localizada en el corto plazo.
Perdona, ¿me lo puede repetir?
Claro que sí. Bueno, entre la principal recomendación tenemos de que el déficit de materia orgánica debe corregirse a través de la aplicación de materia orgánica localizada, pero previamente compostada.
And amongst the other recommendations, it was also concluded that the that there was correct use of organic matter and nutrition deficit, and to promote the use of compost.
Otro dato importante es que no es suficiente aplicar materia orgánica, sino lo correcto es regenerar el suelo. Y para eso se requiere un trabajo a mediano y largo plazo.
Another recommendation that was taken out was that there wasn't enough organic material. There wasn't sufficient organic material to take out these to achieve the productivity.
Así deberían estar las parcelas de quinoa, con bastante vegetación, ¿no? A nivel práctico, en el campo están desertificándose. Así debería estar el 100% de las parcelas.
As you can see in the images, this is how the quinoa land should be.
Eso es lo que tengo para compartir. Y finalmente agradecer a los productores de quinoa, a la Universidad de Encinas, que ha sido el líder de los productores, a los técnicos de campo, a la Fundación INESAT, que ha permitido implementar este trabajo, a la Cooperación Internacional de Canadá. Está inserto, todo este trabajo se ha podido realizar a través de la producción de empleos verdes y agricultura sostenible para el sector de la quinoa boliviana.
This is what I have to share with all of you, and I'm thankful for all the technicians who have worked with us in the fields, and also the International Corporation of Canada, who was one of our collaborators. Also all the technical assistance that was facilitated during this period.
Muchas gracias.
Well, thank you
so
very much, Oscar. Next, I would like to introduce Alejandro Herrera. our learning coordination at INESAT. He holds a master's degree in economics and finance from the Barcelona Graduate School of Economics de la Universidad Pompeu Fabra, a master's degree in economics from the Bolivian Catholic University, and recently obtained a master's degree in philosophy of social science from the London School of Economics and Political Science, where he specialized in the conceptual foundation of causality. In the field of applied research, he worked in the research department of the Inter-American Development Bank in Washington, D.C., and consulted for IDRC Canada, the Economist Intelligence Unit, and Manaus Consulting, among others. His experience combines econometric methods, causal inference, and policy analysis in education, financial inclusion, employment, and agriculture. He is going to speak in English. Welcome, Alejandro.
Well, thank you very much. Thank you, Beatriz. Thank you to all of our colleagues in India. So, as Beatriz mentioned, I'm Alejandro Herrera. I'm part of the Fundación INESAT. I'm an economist, and I'm going to talk about the impact evaluation of the intervention that Oscar designed based on what he already mentioned. So let me start with this presentation. The central question behind this work is very clear, is how can we reliably measure what truly improves productivity under real farming and climate conditions? Okay, so the motivation is this one. Agronomy help us to understand how soil, crops, and climate interact, but maybe on its own, it might struggle to fully isolate what actually causes and also influences yield improvements. So that's why we rely on causal inference methods to solve this problem. It allows us to compare treated and untreated plants in a very structured way, reducing biases coming from soil differences, farmer behavior, and weather shocks. So we basically combine the agronomic methodology that was related with demonstrative plots, and we incorporate some experimental settings that is already very used in economics, in social science, so in order to have some variation, some heterogeneous analysis to understand the variation of the treatment effect among very different plots. So in real environments like the southern Altiplano of Bolivia, full experimental control is almost impossible. That is precisely why this combined methodological approach is needed. Agronomy explains us the process, the intervention, and causal inference, the experimental setting, measures the true impact. This pilot intervention, which was based on what Oscar had previously described to you, and was later implemented in the southern Altiplano of Bolivia, was randomly applied to 18 certified Kima plots. As I'm going to show you later, we observe yield gains between 10 to 20%, with even larger effects in plots that followed technical protocols and received frequent supervision. At the same time, rainfall, frost, wind modify the magnitude of the effect. Maybe that's the most important part of this presentation. And this tells us something very important. The treatment works, but climate and also management of the plot define how much it works. The practical implication of this is very clear. Soil treatment alone is not enough. It must be combined with supervision, climate anticipation, and also natural protection. Let me now briefly describe the empirical setting behind these results. The intervention took place between 2023 and 2024. 18 certified plots were randomly selected, and within each plot, the plot was divided in two parts. A section of plants as a control group without the treatment, and the remaining plants as the treatment group to which Oscar compost was applied. These were real quinoa plots exposed to natural soil variability, rainfall variation, frost, and strong winds. And this is what makes the results especially valuable. They reflect true agricultural conditions, not just laboratory settings. So these maps show the exact location of all randomly selected 18 plots. Here you have the two famous salt lakes in Bolivia, Salar of Uyuni and Salar of Coipasa. So our randomly selected plots are between these salt lakes, and these maps confirm that the plots are geographically dispersed. They face different terrains and climate conditions. So the spatial variation becomes crucial later because it allows us to understand why the same treatment, the compost that Oscar designed and developed, can produce different results across farms, across plots. So before moving to the results, it is important to clarify what exactly we are measuring. So our main outcome is very simple. The weight of quinoa grains per plant measured in grams. This gives a direct and intuitive way to compare productivity between treated and untreated groups of plants. We now move to the core evidence. I'm going to summarize all the results that we have, and I'm going to also show the variation between the different climate and management factors that condition the results. So across all the plots, the treatment group consistently produced more than the control group. The average gain, here you have a graph that is showing the results. The gray bar are the control group, and the green bar is the treatment group over the weight of quinoa grains, grams per bush per plant, right? So the average gain ranges from 10% to 20%, and especially under high compliance. I'm going to talk about a little bit later about that. Under high compliance, the compliance of the protocol that Oscar designed, the effect becomes even larger. At this point, we establish basic results in our research. The treatment works, but it works better when it is properly applied. So when we see this visible difference, the natural question is, are these results statistically meaningful or just they are random? So the statistical tests confirm that these differences are not random. The overall effect is statistically significant at the 10%, but if we focus on high compliance, the productivity gain rises about 15 grams per plant to more than 27 grams per plant. So this reinforces a key message. You can see the different regression models that we estimate, and for an overall effect, we have 15 grams per plant. But if we focus on high compliance plots, those that follow strictly the protocol, the effect is even larger. It goes to 27 grams per plant. So the message is important. Technical discipline and supervision strongly amplify the impact. So having established the overall effect, we ask now a deeper question. How does the environment shape this impact? So as you can see here, we have also heterogeneous effects based on the intensity of rainfall that is divided by the median. So in the left panel, you have those plots and those plants that were affected by very low and very scarce rainfall. And in the right panel, you have the plots that were exposed to very high rainfall, very intense rainfall. So as you can see here, rainfall increases yields for both groups, for treatment and control groups, but the treatment benefits more from favorable rainfall. At the same time, this relationship is not perfectly linear. too much rain can also generate many risks. This tells us that soil treatment and climate do not act separately. They do not act independently. They interact strongly. So we also have some results for cold stress, again by intensity according to the median. Frost reduced productivity in general. However, even under strong frost condition, treated plants still perform better than untreated ones. This shows that the intervention does more than raise average yields. It also increases resilience to adverse climate conditions. We now turn to wine exposure. Strong wines weaken the treatment effect, but they don't eliminate it. Treated plants still outperform the control group, even under high wines. This clearly highlights the importance of natural wine barrier. That was the last point of Oscar. Many local vegetation are also important, and they are also a complement mechanism for the importance of the compost that we applied in these plots. Let me go to the results by farmer presence. At this point, I described the importance of climate factors like wind, like rainfalls, but an important message in our presentation and our study is the importance of the presence of the producer, of the presence of the farmer. So this brings us to one of the most powerful results in the entire study. Plots with frequent farmer presence and supervision show much higher yields, right? The stronger treatment effects are concentrated in those plots that were followed by the same producer. The producer was constantly monitoring the implementation, the process that followed all this process. So, and also the highly significant differences are located where plots have the farmers at constant time, right? So this clearly shows that technology alone is not enough. Human presence, the presence of the farmer, the presence of the owner of the plot is fundamental. The constant attention are essential for this. So let me conclude with the main findings. Then let me describe briefly the results. The treatment increases quinoa productivity between 10 to 20%. Stronger effects appear with the protocol compliance, with frequent supervision and favorable rainfall. Even under frost and wind, treated plants remain more productive. Overall, the intervention improves both productivity and climate resilience. The recommendation from this evidence, the policy recommendation are direct and practical. Expand the use of this treatment among plots that are producing quinoa, and strengthen farmer training and supervision, improve frost anticipation using weather station, as we did with INESAT in the area, and rehabilitate natural wind barriers. These are low-cost, feasible, and scalable action, as Javier is going to explain us in the next presentation. So just to conclude, this study shows that combining agronomy with causal inference methods like this experimental setting in real plots produce credible evidence, better policy guidance, and a stronger climate resilient farming strategies. So thank you very much, Daniya Bhatt, to all my colleagues in India, and thank you for this opportunity.
Beatrice, you are on
your microphone.
I'm very sorry again. So thank you very much, Alejandro. And next, I would like to introduce Javier Aliaga. He's an economist with a degree in economics from the Bolivian Catholic University, a master's and doctorate in economics from the University of Zaragoza and the University of Cologne, and a specialist in development finance from the University of Frankfurt. He is currently a senior researcher at the INESAD and a full member of the Bolivian Academy of Economic Science. He works on issues related to energy economics, environmental sustainability, climate change, and macrofinancial analysis. He has been an international consultant in more than 40 countries and has published more than 50 papers. Welcome, Javier.
Thank you very much, Beatriz. Very pleased to be here with our dearest colleague from India. Let me share, please, my screen. Please let me know when you see my screen.
We can see.
Okay.
We can see
Do you
it.
see my screen?
Yeah.
Okay, thank you very much. Well, what I'm going to do is try to compile all the results from Oscar, from Alejandro, and other colleagues who measure the carbon footprint, the water footprint, the cost of different practices, and try to put all together in two metrics. One is the cost and the other is the effectiveness, and try to see if the cost justify the effectiveness of the practice. The motivation here is planning, is to bridge the gap. We have a very strong problem, which is that in the short terms, we look for financial profitability, but in the long term, we are looking for sustainability, but this is quite complex. There is a paradox of the time of horizons. In the short terms, we look returns, but in the long term, we are looking for sustainability, and we need planning to bridge these two horizons. And one of the main tools is to analyze the cost and effectiveness of different practices. As you can see, is quite dramatically what Oscar has explained in terms of land degradation and water scarcity, and how important is that we have effective practices, as Alejandro has remarked. Our starting point is to map all the Latin American countries. As you can see in the first column, we have several practices such as organic fertilization, crop rotation, and other things. And in the last column, you see the examples of countries that are implemented at the moment, these practices such as Bolivia, Peru, Mexico, among others. And we map costs of these different practices, as this information help us to find some key findings from a Latin perspective. Probably the most relevant is that biological process and practices such as crop rotation, tillage reductions, and things like that has the most relevant cost effectiveness because they have a low capex. Capex means the capital expenditures. So capital expenditure must be low if we want to achieve cost effectiveness. Fertilization, which is our main focus, because I'm connecting the dots of Alejandro and Oscar presentation, is that highly effective practices happens when the opportunity cost of labor is low. So this is very relevant because high capex practices could be an entry point, but in many cases it's not feasible for producers due to their financial constraint. This is like a more detailed explanation, but I'm going to focus my considerations to the conditions that make compost and manure feasible. And probably it's like remarking that low opportunity cost of labor is one of the main preconditions to make a good agricultural practices, cost efficient. And the second one is the availability of inputs, which is extremely complex situation in the case of Bolivia. The inputs to produce compost in Bolivia, it's quite complex, it's expensive, it's a complex logistic to capture all the inputs to conduct the practices. So this is something that we need to improve if we want to make this practice more, to make it more cost effective. In the case of irrigations, what we found is that low-cost irrigations as gravity practices, things like that, has low capex. Again, low capital expenditure. They are more focused on operative expansion, on OPEX. So this is like an entry-level solutions that can be very useful if we want to mitigate droughts risk in the short terms. It's a not long-term practice. It's a short-term practice to stabilize the increase of variability, especially in episodes of drought risk. And what is the idea? The what and the how. What are we going to do? I mentioned before, we are going to put all together more than 20 research in into metrics, the cost and the effectiveness, to planning, to try to bridge the short term and the long term, try to align the incentives in the short term and in the long term. And here is a very, very funny and really terrible draw picture. You see a house and you see a building. Let me believe me, this is a building. So in the short term, you have your house and you spend your money to build your house, and you plan to build a building. But then in the middle, you need to destroy your house. So you need to spend a lot of more money to build building. But if you use the foundation, if you plan in the short term how to connect to the long term, you use the foundation, so you reduce the resources over the time, and this is cost effective. To measure this, what we did is to analyze the carbon footprint, the water footprint, the cost of practices, the soil practices, the carbon practices, the impact that Alejandro just presented, and try to put in a very simple metric named cost-effective ratio. This is the methodology from the life cycle assessment that Lily and myself conduct for soil and water, and we can conduct a fully methodology from the cradle to the grave, but we just analyze the farm gate level, which is scope 1 and scope 3 with this formula. I'm not going to spend much time explaining the methodology. And here is the second methodology with 3 blocks, 3 components: the net present value, the cost effective ratio, the second one, and the incremental ratio. As you can see in the second formula, if we increase the effectiveness or we reduce the cost, we have a cost-effective practice. And if we implement an intervention such as Oscar and Alejandro just mentioned, we can verify what happened with and without this treatment. If the practice has an increase in the effectiveness or reducing the cost, we can find a very interesting incremental cost effectiveness ratio. The idea is that the practice is effective if it's on the red line, and if it's out of the red line, it's not a cost-effective practice. In terms of the compost, what we found is that the cost-effective ratio is 171 Bolivianos per ton of CO2. We are measuring the carbon sequestration, and the increase of the yield is between 20 to 26%. And when we simulate with Monte Carlo simulation 5 times the result, we found that the median of the cost effective is 170 Bolivianos per ton of CO2 equivalent, and it's quite similar. So this is a very interesting practice, not enough to say that is yet a cost-effective solution. When we compare mechanized irrigation with other low-cost irrigation, we can see that the mechanized irrigation increased the yield in 20%, but the low irrigation method it only increased in 12 but the cost is completely different. In the first case is 2,000 bolivianos. In the second case is 800 bolivianos, which is less than the half. In the bottom of the screen, you can see that we can combine compost with mechanizations, and there is like a synergy of 10% of the cost. So it means that the combination of practices could make the better result. Here are detailed explanation of a 10-year horizon in terms of cost and benefit, the cost analysis ratio, and the net value price analysis. I'm not going to explain this because I want to move to a very illustrative figure. Here you can see in my right side of the screen, you see mechanized irrigation, which is out of the line. It means that it's out of the effective frontier. It's very expensive due to the high capex of the practices. You see in a triangle the compost with an X, which means that the compost is quite close to the effective frontier, but not exactly in the frontier. But when we combine compost plus low-cost irrigation, we are in the frontier. It means that the combination of these two practices could be the ideal strategy to create a cost-effectiveness solution that could be scaled up. The other main findings here is what Oscar mentioned at the beginning of his presentation, and at the end of his presentation also, he remarked that we need to recover fertility. It's not 1 year, it's not one shot practices. It takes like 6 years to recover the fertility of the soils. So we need to develop interesting financial tools, blend tools, to support farmers in order to bridge the short term with the long term. My main conclusion and recommendation is that we need a multi-criteria classification on different metrics to have a clear understanding of the situation. First, the second is that compost is a not regret option. It means that it helps food security, climate mitigation, climate resilience, and improve farmer incomes, but it takes time. It takes 5 to 7 years. So we need financial tools that we need to combine solutions such as compost plus low-cost irrigation method. The combination of package will make the better result. So we need to define clear and feasible strategies to upscaling the fertility of our quinoa producers. The same happened with all Andean crops, and more or less it's the same story in Latin America and other crops. We need to combine increasing the yield plus increasing the carbon sequestration plus reducing the use of water, and this combination will lead us to maximize farmer incomes, to bridge the financial profitability and the sustainability, and improve the living condition of our small farmers in Bolivia and Latin America. Thank you very much.
Thank you very much, Javier. Next, we can have some questions and also some comments if you want.
One of our Indian colleagues has a question, so you can go ahead, please.
Thank you. Thank you so much for all presenters. It was really wonderful. My question, I have 3 questions with Mr. Oscar. My concern was that the agroclimatic conditions of your place is quite similar to ours. And you told me that compost making, it's take 4 months. Can you please explain what is the temperature there? And second, why quinoa itself? Because the climatic conditions of India, where I belongs to, it's quite similar to your place. So why only quinoa you adopt? Because if you go for soil fertility, you can go for different crops also, lentil crops, soil fertility regarding or green if you go for the manure type, green manure, etc. Why quinoa itself? And regarding the pH, you are 97%. What does it mean? It's a basic or alkaline, or what kind of you want to share? So these are the three questions I need to know. Thank you very much for all.
Okay, I think I don't know if there is the translation, but
Sí. Ya, señor, voy a empezar con la primera pregunta. Ella pregunta por qué y en qué base está la temperatura cuando se hace el compost.
De acuerdo. Bueno, la temperatura anual de la región del Altiplano Sur, la temperatura promedio es de 8 grados centígrados del
The
altiplano.
annual temperature at the antiplano of the south of Bolivia is 8 degrees, which is
Y
the
en
average.
invierno la mínima es por debajo de 0 grados centígrados.
And during winters, the minimum is below 0.
Adelante con la siguiente pregunta.
Entonces, en base a a su respuesta, pregunta, ¿cómo es posible que se cultive dentro de 4 meses? Porque en base a la temperatura que menciona usted.
Ajá. El proceso de compostaje normalmente se realiza en un año en la región, en el Altiplano Sur.
Perdona, ¿se realiza normalmente?
El compostaje, el año que referí en la presentación, está relacionado al tiempo que dura tradicionalmente hacer compostaje en el Altiplano Sur, un año mínimo.
Okay, so on the basis of the presentation, it said that in the Antiplano region of Bolivia, the process of compost was mentioned in years, in 1 year. Pero ella pregunta entonces, ¿cómo lograsteis hacerlo dentro de 4 meses? Porque normalmente
bueno.
la temperatura, como, sí.
Bueno, hay una técnica en el que se usan microorganismos eficientes.
There is a way, a technical way wherein the microorganisms are used.
También se usan bacterias lácticas.
And also the bacteria, the lactose bacteria are also used.
Tricoderma, el hongo tricoderma también se usa. Trichoderma sería.
Trichoderma, it's in English. Okay.
Trichoderma es en inglés. Bueno, el material que hemos compostado, perdón, el material que se ha compostado es estiércol de ovino y camélido.
Ovino y
camélido. Estiércol de oveja y de llama.
Okay. Ella está interesada en la siguiente pregunta y pregunta por qué cultivaron quinoa y no otro producto.
Esa pregunta es muy interesante, porque en esa zona solo produce quinoa.
He's saying that it's a very interesting question. The answer is that in this region, it's only quinoa that is produced.
Ningún otro cultivo puede tolerar estas bajas temperaturas.
And there's no other product that can tolerate such low temperatures. Yeah, yeah. On the base, because the temperatures are so low.
So we have one hand raised. So we can hear from Dr. Reddy if you have a question. We know we are running short of time, but one last question, if you permit, Beatrice.
Yes. Last question. I think there is some question here in the chat. I don't know if I can read if there is no another question.
So Roberto Jimenez had put a question in the chat box, but I think Dr. Javier kind of roundly responded to that question during
Okay.
his presentation.
Okay.
If there is a follow-up question from Mr. Roberto Jimenez, we can hear him. But Dr. Reddy, do you have a question or do you want us to move on?
Sir, you can move on, sir. You can move on, sir.
Okay.
Thanks.
So thank you very much, Beatrice, for this very informative session from Bolivia. You know, this evidence-based, research-based, and methodologically sound practices that you have presented are really useful. Similar practices need to be followed across the global south for getting effective solutions that then can be shared across global south. Let us now shift to the next session, before which I would like to acknowledge the presence of Mr. Lakshmi Chandra, Undersecretary in the Ministry of External Affairs, Government of India, who is, present with us and taking notes, as our Ambassador Wadhwani had said. So thank you very much, Mr. Chandra, for continuing with us. Let us now shift to the second session. We have lost about 20 minutes or more, but we will try and wrap it up as soon as possible. If not at 8 o'clock Indian time, then maybe another 5 to 10 minutes extra, and begin with Mr. D.V. Singh, as mentioned during the inaugural session. He is from ICAR. We have 3 countries represented in this second session through 4 speakers. So given the time constraint, if I could request each of the speakers to limit themselves to 6 or 7 minutes, starting with Dr. Dharamveer Singh. He is Principal Scientist Soils at ICAR, Indian Council on Agricultural Research. And as I've mentioned, he has expertise in both soil management and watershed management. And the number of, one book and number of co-edited books and huge number of papers that he has published is something that will take more than the balanced time of this workshop to repeat here. So I would just say that he is a very accomplished researcher from India. And Dr. Singh, over to you for about 6 to 7 minutes. Thank you.
Thank you so much, and good evening to everyone. Good morning to rest of them, those who are in the morning in some of the countries. And in fact, first I would like to share my presentation. Share. I am first time using this WebEx. We generally use Google and our what is that? Zoom. What to do in this one? Share image. Windows, Chrome tab, entire screen. No, I'm not getting.
You will see a share option at the bottom.
Yeah, that is
okay. If you click that, it can connect you to your.
But there
desktop.
are 3 things: Chrome tab, Windows, and entire screen. 3 things only are coming.
So you will share your screen.
But that screen, entire screen, it's coming, what it is there on my this thing. Oof, what is this? I will
You
first
press on Windows.
once again.
Sir, on your screen itself, you will find out the share button.
That is there
Click
already.
on that share, you can share your PPT.
Oh. What is this? Either
Are
it
you
is
able to
Chrome
the-
tab, Windows, and this is okay. Whether it is shared now?
No, yeah, it's okay, sir. You can start it. with
Yes, we can see it.
It is moving.
Yes.
Yes, sir.
It is moving. Okay. I will try to give a very brief insight of soil and water conservation practices, and which generally consider as key for climate resilient agriculture. And I will try to give a glimpse of different practices what we have in India, and we have a very diverse kind of things in India, and we have different kind of practices. Before I try to show you those practices, I will have only photographs and some impact of those practices. I would like to tell to every one of you, already soil is under threat, and this particular resource, if you just see, it is responsible for producing almost 95% food of for this planet, and rest of the things I think I'm not going to go into detail. Then again, in India, if you see the degradation as well as in globe, against a very serious problem exists, and almost 120.7 million hectare in India suffer from different degradation problems, and in entire globe, if you see, about 2 billion hectares is suffering from different degradation problems. And major problem here in India, which generally we encounter, or which is operating in India, that is water erosion. Almost 68% of 120 million hectare suffer from water erosion problem in our country. And what are the drivers for land degradation? There are 4 drivers. If you go into detail of these, again, loss of vegetation cover, then landscape disturbances, unscientific land use, and socioeconomic factors. What are the major concerns? I will just try to put before all of you. We have a problem of land degradation in our country. Then we have accelerated soil erosion problems. Then again, we have very high initial cost of resource conservation technologies, and expected increase in soil erosion due to climate change, again, because intensity of rainfall is increasing. Then we encounter with natural disasters like floods, droughts, landslides, flash floods, maybe in other countries as well. Creation of an additional carbon sinks, that is our target. By 2030, we want to meter about 2.5 to 3 billion tons of extra carbon we wanted to sequester, and we wanted to achieve land degradation neutrality in 26 million hectare by 2030 in India. This is our target, and again, we suffer from moisture stress problem in many parts of our country. So looking at these major concerns and challenges, we have several technologies to the institute what I belongs. This is Indian Institute of Soil and Water Conservation here in India. We have 8 centers spread throughout the country. Of course, we work in collaboration with our other sister ICR institutes. We have a huge network of ICR in this country, and of course, that is responsible to have food security in this country. Just for a sake of all of you, if you see soil productivity, that is again reduced by soil degradation, and again it can be enhanced by or improved, or it can be sustained with soil conservation practices. Here in soil erosion, a problem, it is not only physical removal of the soil, but while soil is transported through erosion, there is a huge loss of carbon, and about 20 to 30% carbon get emitted to the atmosphere. So again, there is a this soil erosion is a source for your climate change as well. And if you see the potential with respect to soil conservation, we have almost 45.6% percent of the total carbon sequestration potential what it exists in this country that can be fulfilled by controlling soil erosion in this country. Here I'll straight away come to the strategies what we can adopt for erosion controls. So the first line of defense, it comes agronomic measures, then of course land configuration measures on arable lands, then we have mechanical measures on non-arable lands, of course vegetative barriers, alternative land use systems like agroforestry and other systems, and water harvesting and recycling. So these are the part of major strategies what we adopt in this country. And if you see the conservation measures for erosion controls to achieve land degradation neutrality, again we can classify them in different groups, like promoting in situ moisture conservation, then intra-plot runoff harvesting, then interplot runoff harvesting, safe disposal of excess runoff, runoff harvesting, recycling and groundwater recharge, then erosion control measures for special problems like landslides or mine spoil rehabilitations or mine spoil areas. Then we have vegetation establishment in non-arable lands. So these are the 7 major a group of different soil conservation or soil erosion control measures what we have in this country. And I start with just only with the photographs I will run through, and I'll try to complete my presentation within 7 or 8 minutes. So I'll start with mulching. This is a very effective measure, and generally most of the farmers, they go for burning this crop residues. That is again harmful for our environment. So if that can be used as a mulch, so that is very effective. And if you don't have crop residue, you can go for alternative means like plastic mulching. So that is quite effective for soil conservation and water conservation. When we talk about in situ moisture conservation practices, this is another practice, that is vegetative barrier. And across different sloping lands, we can use vegetative barriers, which provides like a filter. It will arrest your soil upstream sides and safely pass on or pass off the water through these filters, and our productive soils get retained in the field, and we can sustain our soil health in the fields. Then this is again a picture of vegetative barrier in combination with trenching, that is tea plantation. This is again same kind of pictures. And this is another pictures where the vegetative barrier is being planted in sloping lands. So that is quite effective for controlling erosion on fields and sustaining your soil health. This is another picture of your contour cultivation plus vegetative barrier of vetiver. So this is quite common in our Karnataka region. So that farmers, they are getting quite good benefits out of these practices. If you see the impact of covers, the different cover if you have in the fields like fallow land, grass cover, trees plus grasses, you can see significantly impact of these kind of covers on runoff. Runoff get reduced very significantly, and rainfall what you are receiving in that particular area get infiltrated to the soil, and that will improve your soil moisture regimes in the fields. Then if you see the practice of bunding for rainwater conservation, so this is again the practice, mechanical practice for harvesting water, in situ conservation of water. So this is a very widely adopted practice in our country. Almost all the fields, we have field bunds or compartmental bunds, or in some of the areas we have even contour bunds. So this is another good practice of soil conservation, which is quite effective. This is one of the practice which can be adopted if you wanted to convert sloping lands into terraced fields. And if you see, these sloping lands are converted to terrace fields by vegetative means, and different vegetative means like Guatemala grass, or even a combined with the pineapple plus Guatemala, or even geranium sometimes we can utilize as per the climatic conditions, different vegetative barriers which can convert your sloping land to your terraced lands. This is another picture you can see where the terraced lands, you have a lot of area get lost through your rises. So these rises can effectively be utilized by planting different perennials crops like perennial beans, cineraria, that is again medicinal plants, even scented geraniums, or even tea plantation can be established if climatic features or climatic conditions they permit. So we have different criteria as per the suitability as far as the existing land slope, soil depth, rainfall, or what land use you are going to adopt. So we have the decision criteria for selecting different conservation measures or erosion control measures in different sets of conditions. So this is again evolved based on scientific research we conduct in different parts of our country. So this is another very effective measure, trenching. Generally, we follow in non-arable lands, and here again we need to decide what should be the vertical intervals and what should be the size of these trenches. So in different regions, we have different standards, and they are quite effective for harvesting rainwater for non-arable lands. And we have a software for this if any one of you wanted to utilize it. So you can calculate how many numbers of trenches at what size and at what intervals in different slope regions you can very well calculate with this particular DSS. Then you have another measures, stone bundings. So that is also common where stones are available on grounds. So even stones can be utilized for having bundings in your fields, which is quite effective for reducing your runoff and soil loss. This is again combination of your stones plus earthen bunds, and these are also measures quite familiar in many parts of our country for controlling soil erosion and runoff harvesting. This is one of the measures which we call half moon terrace. In degraded lands, in sloping areas, we make small basins like of half moon structures, and we can go for planting trees. Even horticultural plantations can be established. This is another pictures where effective utilization of terrace risers can be done. This is the picture from Nilgiris and Tamil Nadu state of our country. So their farmers have adopted this particular practice, and this particular technology developed from our institute. This is another practice in if you have very a water scarce area or low water or rain-fed areas, so plantations can be done with this technology. This technology is well proved and recently developed from our institute. And here forestry and for horticultures, you have different pit size, and you can go for subsurface planting techniques, having some kind of protocol of this technology. And here in this particular technology, you can have a survival of almost 90%, and that will be almost 34% higher than your normal practice. And even,
Dr. Singh, can you please wrap up now?
yeah.
Three other
I'll just
speakers.
wrap up, sir. So this is a technology of successful planting. Then you have different technologies of soil and water conservation where productivity can be enhanced by 13 to 76%, runoff can be reduced 24 to 76%, and soil loss can be reduced 29 to 93%, and income can be enhanced to 5,852 to 28,000 rupees per hectare. This is some of the impacts of different technologies. Then again, impact of different technologies. Then you have another set of measures like check dams, and even you can utilize the biological material like bamboos for check dams. Then you have the practice of soil conservation agriculture, and here we use the three main pillars of conservation agriculture: minimum tillage, crop rotations, and continuous residue over cover. So this is another good practice. Then agroforestry systems, and finally, altogether, when we take up a landscape-based management, so we go for watershed management. Here we have a lot of opportunities, and if you see the impact of watershed management in this country, we have a very encouraging results, and almost 93 million hectares we have covered with watershed management in this country. We have this now watershed plus approach, In rainfed areas particularly, there we have converse our different schemes like soil health missions, associate missions, agroforestry missions, and national bamboo mission. And if you see the overall impact of watershed programs, so all the parameters of your improvements are enhanced with the watershed management if you compare without watershed management. This is meta-analysis for entire country, 636 watersheds we have studied. This is another technology that is pond linings. If you wanted to reduce the seepage losses, you can line your ponds with the material available and you can have a better impact or savings. This is the technology for Odisha, where Jhola Kundi, this is the name of this technology. The small holders, they can have subsurface water harvesting through this technology. And this is the technology for Himalayan regions, inter-watershed water transfers. So you have watersheds in Himalayan regions there, you have the surplus of water, and you have the watershed where you have the deficiency, and you can transfer these waters from surplus to deficit. And you can see the farmers' income can be enhanced more than 4 times. Then
Thank you.
yeah. This is with respect to micro irrigation. Almost 13 million hectares we have covered in this country, and we have a good impact. Maharashtra is leading with respect to drip, and sprinkler is led by Rajasthan. So we have 9 establishments in this country
Dr.
with
Singh,
respect to soil and water conservation. This is last, sir. And if any
okay.
one of you wanted to connect with us, so we have presence in our country with respect to soil and water conservation. If any question or any collaboration or any kind of help is needed, we will be happy to share. Thank you very much.
Thank you, Dr. Singh. I'm sure there are many questions, but more than that, I think the number of initiatives and the amount of research that has gone into those initiatives which you are mentioning requires a separate workshop of at least 2 hours, if not longer. And also some of the ideas that you have deployed can be useful for the entire global south. You mentioned this software for trenching, for example. Some of these tools that you have developed at ICAR can be useful for others. What we would do is to request any of our partners from the global south who have any questions or any ideas about relating more to ICAR practices, let us know and we will put you in touch with Dr. Singh. Thank you, Dr. Singh. Let me now let me go down south to Sri Lanka. Mr. Chamila Pereira from Sri Lanka has joined us. He is a principal agriculture scientist in charge of water management and soil conservation attached to the Natural Resource Management Center of the Department of Agriculture of Sri Lanka. He has done a lot of good work on development and field validation of micro irrigation based crop management packages for high value cash crops. And also he is involved in national and regional programs, including, serving on the project steering committee as Sri Lankan member under the Consortium for Scaling Up Climate Smart Agriculture in South Asia, which is a SAARC SAARC regional project. Mr. Chamila Pereira, thank you very much for joining us. I'm afraid you will have to conclude your remarks in about 5 minutes, given that we have 2 more speakers. Over to you, Mr. Pereira.
Yeah, okay. Good morning and good evening. I believe that I am audible to you all. Is that? Hello?
Yes, audible. Audible, sir, audible.
Okay. So let me share my presentation with you. Yeah, I suppose it is visible to you.
Yes, it is.
Right. So thank you very much for giving me this opportunity to share some of the experiences we have on soil and water management with respect to Sri Lankan context, and I will try my best to compile this presentation for 5 to 6 minutes. So I will be presenting a success story on soil and water management, that is drip irrigation based high productivity big onion cultivation package. So its slides are moving.
No, it is not moving, but you can go ahead and speak about it.
Okay, right. But it would be better if I have the presentation and slides moving. But I will try my best to compile. Or let me stop. Still not moving, isn't it?
No, it is not moving. You have to flip.
I
the
don't know
next
what's the
button.
issue with that. So is this moving? Okay,
Yes.
so I will do my presentation without that presentation mode. So I will briefly describe about the challenge for the enhanced productivity for big onion, then the introduction to the drip-based package and farm adoption, promoting promising results, few further developments, and finally technology dissemination. So the challenge is the bridging the gap between the realizable potential yield and the farm average yield. So in Sri Lankan context, the farm average yield is about 18 tons per hectare, whereas the realizable potential is about 40 tons per hectare. The real big challenge is we have to bridge this gap, but conserving the natural resources such as soil and water. So this is the conceptual framework we tested to increase the productivity based on drip irrigation system, adding the components of fertigation, split application of fertilizer, organic matter amendment, raised beds, high yielding varieties, and mulching. So this is the package we developed for the drip-based big onion. Package comprises of drip irrigation system, raised beds, then the organic manure, the cattle manure as the organic manure source, and the straw as the mulching source, and a split application of fertilizer through fertigation. The results were promising. We got around 40 tons per hectare of big onion yield, while cutting down the water use 50% compared to the surface irrigation. And we can save the labor in land preparation, irrigation and weeding, and most importantly, save the energy in irrigation. So this is the layout, and we have different options for these layouts, and farmer can pick what is best suited for his field. And this is how the picture after establishing the crop. So this is the aerial photograph of a conventional method, that is sunken-bed method, and this is in contrastingly how the system can be shown in the aerial photograph as you can see. So if we compare the net cultivation area of the drip-based system and the conventional system, so net cultivation area is about 80 to 82% in the drip-based system, whereas it is about 68 to 70% in the conventional method. So we collaboratively worked with some agencies like Interprovincial Agriculture Extension Service, Provincial Department of Agriculture, Mahaweli Authority of Sri Lanka, and Agriculture Sector Modernization Project to increase the adoption of this package in the farmer fields. So this is the holistic progress up to now from YALA 2021 up to YALA 2025. So we have been able to increase the number of adoption like this. So in general, the previous YALA, that is 2025, majority of farmers were able to obtain 40 tons per hectare yield, whereas some farmers achieved more than 50 tons per hectare. Whereas in economic sense, the average profit was around 3 lakhs of rupees per quarter an acre, whereas some have obtained around 5 lakhs of rupees per quarter an acre. So, and also the average bulb size, as you can see, in general, the conventional method, it is about 25 to 30 grams per bulb, but in this method, we have been able to get some remarkable yields such as 55 to 65 grams per bulb. And the success story we disseminated through some TV programs as such. And overall benefit, if you consider the overall benefits, the higher yields and the higher uniformity of the bulbs, then the longer storability, higher water productivity, higher fertilizers efficiency, and lower pest and disease incidents were highlighted. But as the one of the most important factor, the lower input cost for such as labor for land preparation and irrigation, and then the energy cost and the agrochemicals. For example, the cost of production in the conventional method, it's about 95 to 100 rupees per kg. But contrastingly, in the drip-based package, it was around 45 rupees to 50 rupees per kg. So not only the begonia cultivation, the same system can be used to for the true seed production in the Maha season. Not only that, but the same system also can be used in different set of crops such as cabbage, radish, capsicum, tomato for year-round cultivation while increasing the land productivity. So let just briefly look into the further development. That is, the energy is one of the very big issue in Sri Lankan agriculture sector, and solar powered pumping system has found one of the remedial measure for this package as well. Not only that, but also the liquid nano urea produced by the Institute of Nanotechnology. So we tested this and gave promising results. So liquid nano urea could be used to cut down 50% of the nitrogen doses recommended through the conventional urea for fertigation using the drip irrigation system in big onion cultivation without sacrificing the yields. So with the combination of the blending of these tools or the technologies, finally we have come with a package which covers all the 6 climate smartnesses, that water smartness, carbon smartness, nitrogen smartness, energy smartness, climate smartness, and knowledge smartness. So this is now we are trying to adopt using some of the dissemination technologies such as field demonstrations, visits of successful farm fields, then the TV programs, you can use the YouTubes, social media, leaflets, street drama even, and individual meetings with farmers and hands-on training. So with these strategies now, we are adopting this success story in farmers' fields. So with that, I would like to conclude my presentation. I was going in a very rush manner to compile within the time.
Thank you. Thank you so much, Mr. Pereira. That was really fast, but very relevant. And for those who do not know the seasonalities of our region, when Mr. Pereira was talking about the Maha season, what he meant was the season from September to March. Now we have from Africa, we have from the Republic of Guinea, Mr. Mamdou Hafizou Barry. He has joined us after great difficulty. Our apologies, Dr. Barry, for the difficulties you have with WebEx. But thank you very much for joining us, and thank you for contributing to this very important conversation. You can take another 5 minutes. Oh, I don't see him. He's just left. So maybe then while he tries again to join, he's having difficulties, and our technical team is in touch with him. While he's rejoining, I would request my colleague, Dr. Jigmet Yangchan, to, again, spend only 5 minutes, Jigmet, on your presentation. She is from a high altitude area and a dry land area called Ladakh in northern India. And she has done a lot of on the ground activities there. If you could take your presentation through in the next 5 minutes, Jigmat, that will be very nice. Over to you.
Thank you. Thank you so much. Hello, everyone. Very good evening and good morning to everyone. And Julie from Ladakh. As per the concept note, I have to touch this topic. Well, my specialization on soil water engineering, and I'm from Ladakh, which is located above 5,000 meters above sea level, and have to run both of them. Is it not working? Yes. Okay. So as per the concept note, I have to address these 6 parameters: soil degradation and desertification, water scarcity issues, soil health management, agroforestry, solar energy, and soil and water conservation solutions, which we, in the form of success story, I would like to share on this forum. As Oscar already told about their country's agro geographical ranges issues, like similar to our place also, the geographical area is 82,665 square kilometer. The climatic condition was so harsh, dry, cold, and it is known for the cold, arid desert, and where the temperature goes to -35 to +37, and the altitude goes 2,840 to above 4,570 meter above sea level. Next. As Ladakh is located now from country-wise on the top of our country, on the northern part, and we are having 2 districts, that is Leh district and the Kargil district. I got the opportunity to work in entire Ladakh, but today my focus on the very remotest area on a very high altitude, that is above 5,000 meters meter from above sea level, and where the districts, according to the major farming system, we are having 2 farming system, that is agri-horticulture system and agri-pastorals on the basis of soil and topography, into agroclimatic zone as well as when we are talking about climatic zone. It's known for the cold, arid desert. I already mentioned. Yeah. Snowfall is very, when we are talking about precipitation, now the temperature is so harsh, so windy, and it goes to somewhere in -40 also. In summer, in between June, July, only 32 to 35 plus. And the soil condition was sandy soil and very low organic carbon, and water holding capacity is too low. Next. Where, according to the agroecological situation, on the basis of altitude, we are divided this into the three zones, that is upper agriculture zone, central agriculture zone, and lower agriculture zone. When you are talking about 11,800 feet, it means 3,590 to 4,500 72 meters above sea level when it comes into upper agriculture zone, in which only agro-pastorals are survive, because most of these regions, they are nomads. And in central agriculture zone, that is within 3,048 to 3,596 meters above sea level, in which within a 6 month only one crop we can grow. And this lower agriculture zone, it's less than 3,048 meters above sea level, in which we're getting double farming, the 2 crops we can take in the entire year. I got this opportunity to work in entire these 3 regions, but today my focus, when you are talking about soil water conservation measures, my focus on the highest altitude, which is based on the China border, and in this with the upper agriculture zone. Next. In this, and at the same time, the soil type was also a very sandy soil, silt, clay, and clay loam. I already mentioned all. Next. Now, this is the land. This is 4 years back, where around about 4,572 meters above sea level. Here, this area is completely barren, you know. This is 10 hectares land where my challenges in this area, there is a very thin air, no water. Thin air, no water, soil under barren, but it was stony and very limited topsoil. As a expert, soil conservation expert, for me it is a very challenging. This is a scratching where we are doing agriculture. In this area, mostly the farmers are nomads. They are not even knowing how to do the agriculture. You know, for me, that my first concern was to how to do this technology. For that, first my strategy was soil texture, soil erodibility. I have to check. In this, we can come to know that the organic carbon is too less, and the soil erosion is too high because of so heavy wind erosion, you know, because of wind erosion, having a very wind speed is too high. Next. After that, my strategy was water is the biggest issue. In 10 hectares, first time on such a high altitude, first time introduced micro irrigation in 100 canals, you know, and there as Ladakh is full of solar energy, blessed with the solar energy, with the help of this solar panels and submersible oil, we are able to introduce micro irrigation in 100 canals. Next. After that, the main theme is soil temperature is the biggest issue. For that, improving the soil temperature, black mulching, not only reduce the labor cost, but also soil temperature and the water scarcity issue that solve this issue. In this area, I already told the nomadic people, only goat and sheep are there. But for polarization, farm machinery technology, we introduced in 10 hectares, you know. And the soil already, I told that it was soil quality was not so good. For that, vermicompost technology, first time introduced in Ladakh, where it is goes today on a policy level. Now farmers are doing vermicompost technology. It's not only save the time, but it give a very healthy compost within a 3.5 months. Next. At the end of the 4 years back, we get that barren land into green land. Today, where not a single grass can come. Now, watermelon, tomato, onion, brinjal, next, capsicum, and all lentil, millets, potato. And at the same time, this is because one reason I acknowledge to my entire team, I got the opportunity to serve in such a high altitude. On the same time, you all might be knowing Kohinoor. I always said Kohinoor, diamond of Ladakh. This is the world finest fiber, which is known as a pashmina. Now, with the change of climate change, now this pashmina gets reducing. This is the drawback of climate change in those high altitude. Next. These are the soil conservation, soil and water conservation solutions. Drip irrigation we introduced now. Next. Solar energies. Vermicompost. Natural farming, first time introduced in Ladakh. When natural farming, most of the farmers, they are using that cow dung manure, but in Ladakh we are using sheep and goat dungs. And water harvesting is the major solutions for this area. When there is, we are reviving this zinc technology that was a pond system to recharge our water scarcity.
Kindly conclude.
Last is this. There's glaciers. There's on large scale. We are using vermicompost technology. Next. Participation, adoptive farmers is the major key role for them. Training, demonstrations and training we are providing. Scientific visits. Next. Animal health is very important. And at the end, we can say that when we are able to achieve the sustainable development model for those areas. And today, at 5,000 meters, where not a single blade of grass can grow, me and my team able to achieve strawberry, tomato, mushroom in such a high altitude. Thank you very much. One video is also there.
Thank you. Thank you. Thank you so much. You know, this is an example of how even in difficult terrains, technology can help create resilience. So thank you very much. Is Mr. Mamdou there? So Dr. Berry, thank you very much for your patience. You know, Dr. Mamdou Halifu Berry is Director General of the Initiative for Economic Foresight and Sustainable Development, or IPED, from the Republic of Guinea. He's, you know, an old friend of Dakshin, and we are working together on various issues. And I would request him to conclude in about 5 minutes, because we have a number of questions also, which we will spend about 2-3 minutes in responding, and then we will have a concluding vote of thanks. Dr. Berry, over to you.
Thank you so much. I'm sorry for the connection issue. Thank you for welcoming me in this meeting. So thanks to all of you and the attendees. So I'm gonna try to share my screen. Okay, you have it. Okay. So I'm gonna talk about water conservation in Guinea. So as give some examples. Next. Okay, so these are the key points. We're going to have an overview about the Guinean agricultural sector.
Closer to the mic so that
we have
or you can...
only 5 minutes, so we can move to maybe the last point where we talk about water and soil conservation, if you want, because we said we have 5 minutes, right? But otherwise, I can just go through it quickly. So our country has 6.2 million hectares of arable land. And here, as maybe you know, Guinea has is the water tank of West Africa. So we have many rivers that depart from Guinea and go to other countries in West Africa. So we are in we have many water rivers. Next. kind of slow. Next, we can next to the move to the next please. Okay, so the agriculture is facing many challenges like poor condition of transportation, and we got the roads are very very in bad condition, so it's not easy to transport. Like the production, we have low access to land, limited irrigation systems, access to finance. So many problems facing the sector. And now we have the climate change. So it is believed that it's gonna affect like the rice system. So it's important for us to think about climate change. And we have few research agricultural institutions, but these don't have the necessary resources to achieve their goals. Next. I can see, okay. So, but we have a good potential to export banana, pineapples, potatoes, mangoes, and other plants if these problems within the agriculture sector are overcome. Actually, we already export many of these products locally to ECOWAS, like the West Africa region, but we have some problems because of roads. And the main products here are rice and wheat, and domestic production is currently unable to meet the demand. That's why actually rice is the largest imported food item in Guinea, making up almost 40% of all food imports. In 2020, Guinea imported 239 million USD dollars in rice, becoming the 38th largest importer of rice in the world. It is unbelievable because we have a lot of land, that Arab land, as we said before. So that's why we need to change this situation. Next. Okay. So we can move to next because this is for importation, like these are figures for importation of rice and some other things like from India, from Myanmar, Thailand, Pakistan. So we import many things from these countries, including India. Next, please. So here we start using some technologies like this smart irrigation system. Some farmers start using this system like because they want to optimize water usage. Next. Also, farmers have some mobile applications. These apps provide farmers with real-time weather information, market prices, and best farming practices, empowering them to make informed choices. There are some people also using drones and remote sensing technologies like satellite imagery and remote sensing tools. Next, please. This is very clear. Okay, so for water and soil conservation techniques, here we use dikes and basins, like farmers use it to retain water or create basins to store it. Some local communities from the coast use dikes to manage mangrove rice paddies and prevent salt water from entering it. This is a issue here because some people are facing these difficulties because of salt water entering their land. We use also stone barriers. These are erected to slow runoff and retain water and sediment. This technique is then used in some areas. Also, you got drip irrigation. This technique helps to efficiently manage water through direct distribution to the roots of plants. So it helps to reduce water waste. It is then used in some projects in Guinea. Next, please. So we got also lowland development, like we got 4 types of development. The type 1 is the simple partitioning of the lowland area by dikes and leveling of the irrigation channels. Water regulations by bamboo pipes that allow the channels to be filled and emptied. We got also a type 2. This is type 1 supplemented by a drainage network. It generally relies on a central drain to evacuate or supply water, depending on the situation. We got also type 3 development. This is type 2, supplemented by an irrigation network with the water supply provided by an intake. A structure made of local material or concrete is built for the water intake. This is the most widespread type of lowland development and accounts for approximately 75% of the developments carried out. Next, please. So we got the type 4. This is type 3 equipped with a hillside reservoir for water storage, which supplies the irrigation network. This type ensures complete water because it includes a spillway and intake. Its cost is estimated at $640 per hectare, and it represents only about 1% of the improvement made. So for watershed management, as I said before, Guinea has 23 river basins, in which 14 are shared with the neighboring countries. That means Guinea has an important role to play in this region. Like that's why we have to act to well manage the resources, the water resources, in order to help others, our neighboring countries, get water also. So Guinea is a member of Senegal and Gambia and Niger River Basins Organization. So we got 3 river basin organizations where we are members. Many projects are being developed in these areas, including water management, dams, agriculture. So we have innovative solutions going on for water in rural areas in Guinea. Like we are using solar powered water pumps, rainwater harvesting systems in some areas, and fog harvesting also. Next, please. So thank you for your attention. I'm sorry for the connection. This is very, very low here. I don't know what happened. Thank you.
Thank you. Thank you very much, Mr. Berry. Thank you for informing us of the challenges of Guinea, but also more importantly, you know, the previous speaker talked about techniques to be used in highlands, and you have talked about various techniques that are required to be used in lowland. So this is the kind of, you know, dissemination of knowledge and sharing of knowledge that we propose to do in forums like INESAD and Dakshin. We have some questions on the chat box. So one question by Mr. Ruben Colau regarding whether quinoa is produced in India has already been answered in the chat box. You know, it is not as much in production, but we do produce it and use it produce it in rain-fed, semi-arid and marginal lands. There is a question from Mr. Roberto Jimenez for Mr. Pereira from Sri Lanka. The question is, how did you determine the priority practices in your agronomic management package for onion production and improvement? So, Mr. Pereira, maybe you can respond to Mr. Jimenez.
Yeah, sir, could you please repeat the question? Some of the parts I am not that clear, please.
Yes, so the question is about your onion production and improvement management packages. So the question is, how did you determine the priority practices for your agronomic management package for onion?
Yeah, exactly. So the number one priority is given to the drip irrigation system, not only the water, but also the fertilizer application or the fertigation. They are the key aspects of this package. And then come the raised beds. And some farmers are adopting mulching, but some are not. But to my knowledge, number one, drip irrigation system. Secondly, the fertigation. They are the key components to increase the productivity in this package.
Thank you very much. So we come to the conclusion of the 2.5 hour workshop. We are sorry we took it longer. It is more than 30 minutes behind schedule, but still I think Dr. Sivasena Reddy, who has organized everybody around this workshop, deserves some words of thanks. And also, I am not sure we can conclude or have concluding remarks given the time constraint. But Dr. Reddy, over to you, and then we can give the last word to Dr. Beatriz Hernandez. Dr. Reddy.
Yeah, thank you, sir. Thank you for your appreciation. Thank you for yours. And as the literature says, soil and water conservation is about sustaining the harmony between people and the land we depend on. So today's workshop discussions have underlined that soil and water are the fundamental basis of agriculture production systems, livelihoods and ecological resilience. And first session we have from Bolivia, beginning with soil fertility analysis in organic quinoa production. And the presentation showed clear links between soil fertility and cost-effective interventions. And in the second session, we have comparative experiences from different agroecologies across the wider global south, like India, Sri Lanka, Guinea, and the Himalayan region. And with this, on behalf of Dakshin, the Global South Center of Excellence at RIS, I would like to express our sincere thanks to all the speakers for sharing their insights, time, and to all participants who have joined this session. And we are grateful to INISAR Bolivia for co-organizing this workshop and for the partnership. So we look forward for continuous cooperation. Thank you. Thank you, sir.
Please.
Thank you. Well, thank you very much for this kind invitation. I am very, very happy to share with you our knowledge and to learn of you, of other countries. It was very interesting. I think I learned a lot, and I hope that this is not the first time that I hope that we can, in the future, we can continue with these collaborating issues, sharing our knowledge. And thank you very much.
Thank you very much. You know, we are going to produce a report out of this, which we can, get back to over time and look at the various presentations and the discussion and see what way forward Dakshin and INASAD can draw out of it. Dakshin and INASAD are already working on 2 or 3 proposals for projectizing some of the ideas that we have thought of together. We would move towards that stage shortly, but before that, we'll come up with this report. And all of the speakers who had PowerPoint presentations, if you have not already shared, kindly share them on the emails that have been sent to you, so that our Dakshin team can use them in preparing the report. And we will share and circulate this report to all the participants as well as the speakers. So I thank you very much for your patience and would like to now close this virtual workshop. Thank you and have a good day in Bolivia, and have a good day in Africa, and a good evening here in Asia and India. Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye-bye.
Bye bye. Thank you.